Hello, my name is Alexander Kim, and today I'll be presenting on my Stanford project on the stock market and time series forecasting with TensorFlow. So just a few quick notes before we get started. The first is that some words may sound unclear in this recording. That's mainly because my computer, so I'm recording on right now, tends to muffle up some words sometimes due to unknown reasons. And so I suggest raising the volume to clearly hear all the words. Secondly, code is run on Google Colab, so this means that I get free access to GPUs for faster training, but I will need to upload files from my local device since all the code is actually run on Google's cloud servers rather than my local machine. Lastly, nothing in this presentation is meant to encourage the trading of stocks. I will be going over some technical indicators, but they are not 100% accurate, and securities should be bought at your own risk. So there are three main goals for this presentation. The first is to understand three technical indicators. Second is to understand time series forecasting. And the last is to train a neural network to predict tomorrow's closing price. So technical indicators, what are they? Well, technical indicators integrate both the past and current data. So this includes things like closing prices or volume, which is how many shares were traded within a certain time frame. Now, using technical indicators, traders can predict both the price direction and the price speed. This includes where the price will go and how fast it will go in that direction. So collectively speaking, traders predict price velocity. So we'll be going over three technical indicators, the first being the relative strength index, or RSI, the second being the moving average convergence divergence, or MACD, and the last being Bollinger Bands. Now first off is the relative strength index, or RSI. RSI is 100 minus the quantity of 100 divided by 1 plus relative strength, and relative strength is the sum of the gains divided by the absolute value of the sum of the losses. The key points here are that the RSI measures current price value, and normally the period is 14 days, and the RSI is always between 0 and 100. And here's what I mean by the current price value. When the RSI is over 70, such as here, the stock is considered overvalued and the price tends to go down. When the RSI is under 30, such as here, the stock is considered undervalued and the price tends to go up. So we'll be going over three technical indicators, the first being the relative strength index, or RSI, the second being the moving average convergence divergence, or MACD, and the last being Bollinger Bands. Now secondly, we have the moving average convergence divergence, or MACD. Now the MACD is the H-day exponential moving average minus J-day EMA. And the second line, called the signal line, is K-day EMA of the MACD line. Now today's EMA can be calculated recursively as yesterday's EMA multiplied by 1 minus alpha plus alpha times today's price. Alpha is 2 divided by the period plus 1. Now period could be H, J, or K in this case. Now you can see that there's more weight being placed on today's price than the previous days. And this is because the exponential moving average aims to place more weight on today's price than a simple moving average would. A simple moving average would simply place equal weights on all of the prices that it is taking an average of. Now the key points here are that the MACD detects trend reversals, and normally H is equal to 12, J is equal to 26, and K is equal to 9. So how does the MACD detect trend reversals? Well, if you see at points of intersection between the MACD and the signal line, you can actually see changes in trends. You see a little bit at the end here. And this works because the MACD line will actually react more quicker to trends than the signal line. This is because the signal line is actually a moving average of the MACD line. So for instance, the MACD line goes down here more quickly than the signal line. So whenever it intersects, it may signal a trend reversal. So we'll be going over three technical indicators, the first being the relative strength index, or RSI, the second being the moving average convergence divergence, or MACD, and the last being Bollinger Bands. Now lastly, we'll look at Bollinger Bands, which is trademarked by John Bollinger. There's the upper and lower band, which are calculated as the H-day simple moving average plus or minus the multiplier M, multiplied by the H-day standard deviation of the closing prices. So the end-day simple moving average for today is simply the arithmetic mean of the previous end days of closing prices, and this always includes today. Now the key points here are that Bollinger Bands measure price volatility, and normally H is equal to 20 and the multiplier M is equal to 2. And by volatility, I mean the fluctuation and the changes of the closing prices. So for instance, when the Bollinger Bands are close together, such as here, this means that the prices before it had a fairly small amount of change. And this increases the likelihood of a change in price. So we'll be going over three technical indicators, the first being the relative strength index, or RSI, the second being the moving average convergence divergence, or MACD, and the last being Bollinger Bands. This is a big warning. Technical indicators do not guarantee anything. They do not guarantee a certain trend, for example. So when trading stocks, you must do it at your own risk. Alright, so what is time series forecasting? Well, time series forecasting on the most basic level utilizes a time series dataset. Now, a time series dataset is going to consist of data points that are equidistant from each other. And time series forecasting is going to utilize this time series dataset and predict future oscillations, which would be tomorrow's closing price in this example. So now we can actually get started with the code. We'll start with pre-processing the data. I won't voice over this part because of time, but I will have a few key points listed on the screen where I think some explanation is necessary. So now we know that we'll be using a neural network, but what will it actually look like? So as I've slightly said before, we're working with sequence data, and recurrent layers do make sense in this type of situation. And this is mainly because recurrent layers can combine both previous information and the current information it is on in the sequence. So we'll start off with a GRU, or gated recurrent unit, and they'll add another GRU for complexity, and then we'll add a dense layer along with the dropout operation and two more dense layers. So we can actually get decent results with this model. As you can see, the numbers aren't horribly bad, but there's a way to upgrade this, and one idea is to add another dense layer dropout operation and two more dense layers. We'll actually concatenate the output here, and then we'll run this through another dense layer. So the idea here is specificity plus generality. So taking the specifics from the gated recurrent units, and then we're adding a general idea taken from the dense layers. So now we need to define our model. So start off with the first GRU layer, which is going to have 512 output features, and it's going to return sequences so that we can feed it right into the second GRU, and also return its hidden state, which is essentially just what it remembers from the sequence that it sees. you can see the same settings for the second GRU, and then we'll pass that into the first set of dense layers. Now for the second part of the model, we have the second set of dense layers, the concatenation layer, and the output dense layer. Now we set our initial state, and then we pass that into the first GRU. And then we'll return states, I'll actually feed that right back into the second GRU. And then we'll return states from that GRU, and then we'll actually return that if needed. And then we'll take that output, and then pass it into the first set of fully connected layers with the dropout operation. And then we'll do the same thing for x underscore. And then we'll concatenate x and x underscore. Then we'll pass it into the output dense layer. So let's instantiate the model, and then let's compile it using the SGD optimizer with a learning rate of 0.001 and momentum 0.9. We'll use the mean squared error loss function. We'll set the checkpoint path, we'll define the checkpoint callback, and then we'll train for 30 epochs. As you can see, the final loss turned out to be around 0.0023. So before we evaluate the model, we'll need to get the needed data and labels from test dataset. So test dataset is essentially just a list of input and label sequence pairs, and each sequence has 30 days. So we can actually iterate through all the input and label pairs inside the test dataset and just get what we need. So for data, we'll only take the inputs, so the input sequences. And then for the label, we'll just take the last day's closing price. And then for the full label, we'll take all 30 days closing price. So we'll set return state is equal to true, and then feed in the states, which is none. And then we'll actually see that I'll not be using the states again in a for loop, but outside of this example, it will become very helpful to have this return state equal true option in case you want to run this model in a for loop, and then you want the model to predict multiple days in advance rather than just tomorrow's closing price. So you can see here that predictions is going to be in this shape, but then after indexing, it will be just a list of predictions. Now you want to specify mean and standard deviation, and then unscale the values. Display the mean, standard deviation, and the median differences. And you can get this just by subtracting a label from the predictions, taking the absolute value, and then taking the mean, standard deviation, and median of those values. So you can see that this model is actually much better than the one that I showed you before, where we just use the single stack of dense layers. But a thing to note here is that I'm actually using the absolute value of the differences, which means that it's not taking into account which direction the model thinks that the closing price is going to go. So I measured the increase-decrease accuracy, which measures how accurately the model predicted whether the price is going to rise or to fall. So for the predicted increase-decrease, I'll zip up the predictions and the full label. So for prediction and label in the zip, I'll take the difference between the prediction and the second to last label, and then if it is positive, I'll place a 1. If it's negative, place in -1 for a decrease. And then I'll do the same with the increase-decrease, except I'll only use the label and full label. Now we'll just increment this increase-decrease accuracy by 1 as we iterate through this predicted increase-decrease and increase-decrease. Now we'll set the increase-decrease accuracy to be divided by the length of the increase-decrease. So this actually gives us a percentage if we multiply by 100. You can see for this model, the increase-decrease accuracy was around 51.57%, which essentially means that the model is guessing whether the price would increase or decrease. So I actually ran through that 10 times, so there are 10 trials. Everything was the same except that most of the things were placed within a for loop. So you use empty lists and then you append training losses, means, standard deviation, medians, and increase-decrease accuracies so that we can measure the average across 10 trials. So I actually did this using 3 different optimizers. Now for the first one, using stochastic gradient descent, as we saw earlier. So over 10 trials, we actually got around a 30-cent average difference, around a 45-cent standard deviation, and 15-cent median difference. And our increase-decrease accuracy was 15.91. So secondly, I chose RMS prop with a learning rate of 0.001 and a momentum value of 0.9. Average difference around 37 cents, standard deviation 48 cents, median difference 24 cents, and increase-decrease accuracy of 49.41%. Now lastly, I used Atom with a learning rate of 0.001. You can see for the average difference, 34 cents, standard deviation 46 cents, median difference 19 cents. Increase-decrease accuracy 49.22%. Now overall, you can see that SGD with momentum was the overall winner. You can see second place was Atom, third place was RMS prop. You can see that the increase-decrease accuracy was fairly similar, around 50%. Now here are the loss values for each of the 3 optimizers. You can see on the right, I excluded the first epoch. You can see that the SGD has the highest loss, but it still performed the best. So what were the sources of error? First possible source of error is a simple model architecture. Clearly, the model could be more complex and could yield better results. Secondly, there was a lack of features. We only used 4 columns: closing price, RSI, MACD, and Bollinger Bands. Clearly, there are more technical indicators than those 3, and we could have more features. Thirdly, we only used certain S&P 500 companies, so there is a clear lack of data considering the vastness of the stock market. Lastly, the stock market is extremely complex with many influences, and this was a fairly naive approach. And that's it. Thank you for listening.